Hey again. So today we're going to be doing equilibrium constants, and an equilibrium constant is just a number that we can get from dividing the products and the reactants. Now, what is an equilibrium constant? Well, it was found that during an equilibrium reaction, or during an equilibrium, the ratio between products and constants remains constant. The ratio between products and reactants remains constant, even when a change is placed on the reaction. So what we have here is our equilibrium constant, which is in other words called Keq, and it is the concentration of the products divided by the concentration of the reactants. And even if the concentration of the products changes, the concentration of the reactants will change proportionally so that the Keq always remains the same number. Very, very, very few things can change this Keq value, and we'll talk about what can change this Keq value. So anyways, through experiments, we have found that Keq equals concentration of products over concentration of reactants. So here we have an example of 2A plus B forms an equilibrium with 3C plus D. And what we can do is we can find our Keq, or make our Keq expression, and that would be products over reactants. So in other words, products, which would be the concentration of C cubed, because we have 3 C's. We have 3 C particles, so we're going to cube it, and we're going to multiply that by our concentration of D. And then we'll also have our concentration of A, but since we have 2 of them, we square and times the concentration of B. Okay, so again, even if it's something like the concentration of the reactants is changing and the concentration of products is changing, they'll change proportionally, so Keq always equals the same. So let's say we have a lot simpler reaction of just reactants make products, and they have formed an equilibrium. And now the reactants, so here is our reactants and here is our products, and they have formed an equilibrium. Okay, and so from this, if we take this number right here, this products number, and we divide this concentration by the reactants number, we'll get some value. Now in this particular case, products is much, much lower than the reactants, so therefore our Keq might be something like, let's pretend our Keq equals 0.3 or 0.33. It's about like maybe a third of this height. So our Keq for this pretend reaction right here is 0.33. Now let's pretend we increase the concentration of reactants. So the concentration of reactants goes up. Therefore, it is going to shift right, and the concentration of products is going to go up. So concentration of products is going to go up, and it reaches a new equilibrium, and the concentration of the reactants is going to go down. But before it goes down, we added reactants, so the concentration went up, and then the concentration went down. And what we should see is that the products divided by reactants, well, this height is roughly about a third of, should still be a third of about this height, and our Keq, so our Keq over here, Keq over here is 0.33, and over here our Keq would also be 0.33. Okay, so Keq is not changing. Now, something that will change Keq is if you had something like this. Reactants form an equilibrium with products, but it happens to be an exothermic reaction. Okay, and again, here is our graph. So here is reactants and here is products. So reactants is there and products is there. So right here again we have maybe a Keq of about 0.33. Now if the heat is decreased, so let's pretend the heat right here is decreased, that means our reaction is going to shift right again in order to increase the heat, and that means reactants are going to be used up, in order to make more heat energy, and that means products are going to go up. So what we see here is that at the beginning Keq is 0.33, and over here Keq is, well, Keq is going to be products divided by reactants, and they're getting very, very close to having being closer to the same. So Keq in this case would be greater than 0.33. So Keq would be greater than 0.33. Now this is one of the few cases where the Keq value will change. Okay. Now, so one of the things that you can say is Keq will change because of temperature, and we'll talk a little bit more about that later. But other than that, concentration, pressure will never ever change a Keq value. Okay, so let's get some practice writing some Keq expressions. So again, Keq, just so we don't forget, let's write it up on this corner. Keq equals the concentration of products divided by the concentration of reactants. So again, this symbol, these square brackets, these mean concentration. So here we have a Keq expression. Now, so what is our Keq going to equal? Well, concentration of our products divided by our concentration of reactants. However, what we see here is that one of the products happens to be a solid, and the reactant also happens to be a solid, and this one happens to be a gas. So with a solid does not have a concentration. A solid has a density. A solid has a fixed concentration, and since solids don't have concentrations, they're not part of our Keq expression. So what would it be? Well, this would not be part of our Keq expression because this has what we call a fixed concentration that can't change. This also doesn't have a concentration, and only the gas is going to have a concentration. So our Keq expression is going to equal the concentration of CO2. Okay, and what we see here is we have something very, very similar. We have another solid, okay, and another solid over here. So our Keq formula is going to be this gas, but another thing too is we also have a liquid, and a liquid also has a fixed concentration. A liquid is a pure thing, it is not diluted, and therefore a liquid has a fixed concentration, and this liquid won't be part of our Keq expression. So our Keq formula would be concentration of C2H2. Now, what we see here is we have some more liquids. Now, this one is a bit of a special case, and that you should always try to remember, and that is if you have more than one of these liquids will dilute each other, and therefore, since you have more than one pure liquid, these liquids will dilute each other, and these liquids will cause a concentration of each one. So this one you would count. Now this is a bit of an exception, but it would be the concentration of C6H5Br times by the concentration of HBr divided by the concentration of C6H6 divided by the concentration of Br2. Now again, since the liquid is on both sides, they're going to dilute each other, and therefore they're going to have concentration. So let's take some notes here. Solids are not in our Keq expression. And liquids are also not in the Keq expression. However, an exception is liquids are part of the Keq expression if a liquid is on both sides of the equation. Okay, so again, solids are not in the Keq expression, never in the Keq expression. They're never in there because they always have a fixed concentration. Liquids are not in the Keq expression. However, liquids are a part of the Keq expression if a liquid is on both sides of the equation. The reason being is because these two liquids are going to dilute each other. So Br2 is going to be diluted into C6H5Br, and C6H5Br is going to be diluted in C6H6 and Br2. So they will be diluted and they will have a concentration. And that's one of the a little bit of an exception right there. Okay, and that's how we write our Keq expressions.